Okay, for this section, I'm going to walk you through the complete LSRL analysis. So this is going to walk you through start to finish the 4 steps of what needs to be included in the complete analysis. So I actually already completed this over here, and I'm just going to share this with you and walk you through any questions you may have about what needs to be included in each section in order to receive full credit for the LSRL. So for step 1, we need to talk about randomness, variables, and biases. So for this one, I did not tell you. So if you go back to this problem, there's nowhere in this problem where I said, here's how we got the mother and daughter height. So you're going to have to make that up. And let's assume that we made it up in a proper way. So we took a random sample. We used a simple random sample to generate names from a computer, which is a sampling method. Just a quick note, you could do stratified, clustering, or systematic as well. So when you guys are doing your own, you're probably going to have to use one of those. But keep in mind, I just chose this one for simplicity to just use a simple random sample with a computer. We did this for 8 sets of data with a mother and daughter, trying to see if there's a relationship between the heights of the mother and their daughter. So notice I talked about how I got the sample random, as well as the heights and what I was trying to prove, which is I was trying to show that there's a relationship between the mother's height and the daughter's height. I also talk here, we limit our variables to mother and daughter with normal heights over 6 feet tall. So I'm including here what variables I would consider. So for this one, I'm just considering what we would call normal heights. Now, again, if you want to say 6'2" is abnormal or not, whatever, this is just kind of an example problem, but we're limiting it to, what I would call typical heights. And I'm not going to walk around trying to find, mother-daughter pair that are 7 feet tall. I'm not doing anything like that, just looking at normal heights, normal conditions. The other thing in this one, there's really no sense of bias. If you're asking people about their weight or about their age, you might see a bias. But if you're just saying how tall are you, you could just go and measure them. So there's no sorts of bias in this question. So that's what needs to be complete in step 1, all of that information, your variables, your bias, how you took the random sample, and what you were trying to prove. Step 2 is on your Excel sheet. So this is where you go and get your scatter plot and your residual plot on your Excel sheet. So I already did them. I saved some time. You guys need to go do them. If you need to go back and find the other video of the LSRL to see how these are done, go back and do that. Now, step 3 is analyzing the residual plot in the graph and what all of this stuff means. So based on residual plot, we conclude we have a linear correlation. The reason why is those points are scattered evenly around this line. That means it's a linear correlation. The line of best fit will work about 52% of the time. That's because of our R squared is 0.52 or 0.526. We could probably assume it's because the other 48% of the time resembles a father height more closely. So what I'm doing is kind of introducing some sort of reasoning for why that is about 50%. Let's say you got 10%. Well, the reason it's not scattered, the reason there's no correlation is fill in the blank. If it's 98%, it's a strong correlation. And why do you think so? You also need to make a statement about what is your line of best fit y-intercept. So the y-intercept here is 22.7, which means if the mother height is 0, the daughter's height is 22.7. So that's what it means in terms of context of the problem. Obviously, there's no height of 0 for somebody, but it starts at 0, and the slope in this case means that for every inch we go up from 0, the daughter's height is going to go up 6.64 inches. So that's what needs to be in step 3. Is it linear or not based on the residual plot? What does the R squared mean? Slope and y-intercept. There we go. Then we just write a simple conclusion. We conclude there's a good linear fit for mothers and daughters' heights with the expectation that we will be accurate around 52% of the time with this prediction. There are no real outliers in the problem to throw off the data. So one of the things that also may happen is, let's say you have an outlier that's way out here and thrown off the data. You can remove that outlier and recalculate your data. But don't ignore it. So if you remove the outlier, so for example, this dot right here. So if I go to my prediction here and I have 63 and 59. So if I go to the mother-daughter's heights and I fix this and I take away the 59, 61, no, this would be, if I take away this right here and notice this went up to 84%. So if you wanted to take that away, you could, but then you would say we removed one outlier from our data and we improved R scatter, or R squared, to 84%. So again, it fixes it up here. So I can just click update. So you can do that. So if you removed an outlier, we removed our outlier, moved to 84%, but also indicate what the outlier was. This was a mother with a height of 63 inches, and then the daughter was, say, 58 or whatever it was. So you're going to include that. And then you could also write, and I'll put ... You can write an explanation for why you think there was such a discrepancy in this. And that could simply be maybe the daughter and mother's height was more closely related to the father. Now, if you didn't want to remove that outlier, you could go back a little way and just stick with your prediction here. So rather than saying I removed the outlier, you can just stick with your original set of data, which is the 52.6, and just say it's about a 50-50 prediction. Hope this helps. Good luck.